Hi, my name is Claire Shu and I'm from San Jose, California, and I'm so excited to share my research project, NeuroPlasmaNet, a non-invasive blood-based early Alzheimer's detection using sex-specific brain-blood graph reinforcement learning. Alzheimer's disease, or AD, isn't just an aging disease. It starts taking root decades earlier with cases as young as 19 years old. Women face twice their risk, and half of the AD cases are in the early stage when intervention matters most. However, current detections like spinal taps and PET scans are invasive, costly, and impractical for the general population's mass screening. With an annual healthcare burden of $360 billion, it's now time to shift from reactive care to proactive detection and prevention. Here's where my solution NeuroPlasmaNet comes in, a non-invasive blood-based AI system to detect early-stage Alzheimer's before major symptoms like memory loss and behavior fluctuations set in. I first performed quality control with data preprocessing and normalization, and then removed confounding factors. Since AD is defined in the brain and to be detected in the blood, brain-blood genes form a natural network. And so, I built a sex-specific graph neural network to reveal gene co-expressions and interplay. In the case of TREM2, a gene encoding microglial receptor associated with increased Alzheimer's risk, the GNN captures strong co-expressions with genes such as C1QB, which has been implicated in synaptic loss. It increases their weight, reinforcing patterns of early neuroinflammatory signaling and synaptic disruption relevant to early Alzheimer's detection. Meanwhile, for the housekeeping genes like GAPDH, the GNN downweights their influence due to low variance and limited disease-specific relevance. The two blue lines show the genes that mutually strengthen over every epoch, whereas the housekeeping gene in gray is not strengthened and thus removed from the candidate gene set. Every epoch, or AI learning cycle, is fine-tuned with biological pathway insights and cosine-based rewards to accelerate learning and boost accuracy, which is like embedding wisdom of thousands of biomedical experts into my AI. In the brain, I found sex-specific potential markers and known therapeutic targets, and then correlated these markers to the blood. These NeuroPlasmaNet innovations addresses three major gaps in current Alzheimer's research. The first one is that painful spinal taps and costly PET scans are now replaced with simple blood tests. The second is that most AIs ignore sex differences despite females being twice as likely to develop AD, which I address by modeling sex-specific brain-blood network. And third is, beyond just data, I use AI reinforcement fine-tuning with biological guidance. I've also presented my findings at a seminar. Our body hosts 86 billion neurons with around 100,000 RNA transcripts in each neuron. For example, the CACDA1 gene relates to the circadian disruption pathway, like, do we get enough sleep last night and do we sleep well? And there's also the GRIN2B gene dysfunction, which relates to substance addiction, and this is why we should say no to drugs. And there's also the SOLT1E1 gene, which associates with toxoplasmosis bacteria disease, commonly found in undercooked meats. And these undercooked meats are also found in a lot of European and also American cuisines. As a result, NeuroPlasmaNet demonstrated 92.03% accuracy and identified 12 major marker genes for early detection and potential therapeutic targets, which aligns with known medical research. Since NeuroPlasmaNet reaches 75% of the population, my research could benefit 255 million people in the US alone between the ages 20 and early stage AD. The bottom line is that Alzheimer's doesn't necessarily start at 65. It starts in our youth, so we need to act fast now. Thank you so much for your time, and I'm looking forward to seeing you at CSEF.